Welcome to breadboarding. In the previous video we managed to get our character generator ROM outputting the character set information to the display here. Although at the moment we don't have any video RAM connected up, we're going to be hooking up the video RAM in the next video. But during this video what I'm going to be doing is configuring the PLD here, the complex PLD, so we can output the different attributes. So this will be different foreground and background colours and whether we have blinking video or not. This is video 14 in the Breadboard PC 8088 version 2, and this is part of our plan. We've already developed a basic nanocomp with an LED display and keypad and built-in monitor, and then this is the later stages of our basic floppy disk PC. In a couple of videos time we'll be adding the floppy disk controller and booting MS-DOS from floppy disk, and then we'll be adding a disk controller trying to boot MS-DOS from hard disk, enhancing the video controller to do graphics as well, add a mouse and then try and run early versions of Windows. So this is the block diagram that we've been working from to show what chunks of the project we'll be doing in each step. Now for step 3 we've already done these two steps already. In the previous video we added the character generator ROM and the shift register, but because we don't have any video RAM at the moment, all we're doing is we're feeding in the CRTC address line outputs into the ROM here, and it just generates the test pattern that we showed on the earlier screen. And in this video, we're going to be adding a number of functions. Now, in the version 1 of the Breadboard PC, these were all done by separate chips, separate programmable logic devices and registers. However, what we're going to be doing in this one is combining all of these functions into a single complex PLD, and we're also going to be feeding in the register address lines here into the attribute latch here so that the colours, foreground and background will all be driven by the same signals we're using for the character generator. We're going to be adding the CGA control and colour registers and the status registers as well, so this is all going to be built into the same complex PLD. And what we should be able to get out of here is we should be able to get a modified test pattern, so a bit like the black and white one that we had previously, but with all the colours and potentially blinking attributes as well. So all these functions in orange here are going to be handled by our ATF 1508 complex PLD, and we're already making use of some of that for the clock functions already. And as far as the memory map is concerned, we're just going to be using the standard I/O port ranges for the control port, color port and status port. So let's take a look at some of the information from the original IBM PCXT technical guide to do with the CGA status port and the color select register. The color select register allowed the screen area around the main text area. So on a TV or an old style monitor, then in fact there'll be an area around the text which you could change the overscan colours to determine what that colour was, so in particular for games and things like that, so that the surrounding area would match the background to the game. Now in fact in the documentation here it's a little inaccurate in that the overscan colours is not just 40 by 25 but is also doing the 80 by 25, and in fact there is a bit down here which is known as background intensity. Now this, it says, selects the background colours for the alphanumeric mode, and in fact this is not correct according to the circuit diagrams that we've got that we'll be looking at in a minute. And so really that background intensity only really covers in the graphics modes, and there's also a bit here which is used to select between the colour palettes used in some of the graphics modes. The only real area that will be affected for looking at text modes here is the overscan colours, so really the colour select register is not going to be of too much interest during this video, just because using modern VGA video capture hardware and LCD monitors doesn't tend to show that overscan area anyway. Then the mode control register, this is how we can control what video mode the CGA adapter is running in, so whether or not we run it in the 40 column wide character mode, the 80 column text mode, whether we run it in the 4 color graphics mode or the high resolution 640 by 200 2-color mode. There's a few things here about the values here. The references on the right here in yellow, these are what the schematics tend to use for these particular signal names. So the enable blink attribute, if this is 1 then blinking will be enabled. The 640 by 200 black and white mode. This is to enable the high resolution 2-color graphics mode, which we'll be looking at later on in the series when we add the graphics. Enable video signal or video enable is necessary that by default, unless you put a 1 on this value, then you won't get any video output. And then the original CGA card, then because there was a certain amount of flickering because of some of the video timing with accessing the video RAM, then the IBM recommendation is you disable the video signal before you update the video RAM, and then you enable it afterwards. And we'll be looking at that as we go through the next couple of videos. We'll be seeing that we get video snow or interference on the screen as we update the video RAM, and we'll be looking at how to resolve that using some more complex logic in the PLD. The select black and white mode on the original CGA card, black and white mode would turn off the composite video color when going out to a TV or a composite monitor. On the original CGA digital monitor, then the black and white mode wouldn't actually do anything. But in the previous series, what I did is change the video DAC color palette to be sort of 4 grayscale values. So if we enable black and white mode, we should get grayscale output. Then this next one is how we control whether we're in text mode or graphics mode. So if graph is in 0, then we're in text mode. If it's graphics is set, then we're either in 320 by 200 4-color graphics or 640 by 200 2-color graphics. We switch between the 4-color and the 2-color with this value here. And the high res determines whether or not we're in the 80-column text mode or not. Now, in the original CGA card, all the graphics modes were actually done using the 40-column timings. However, I'll explain as we go through, it's easier, in fact, with this design to use the 80-character timings for the graphics mode because of some simplifications I was able to make in the design. So we're going to be adding these 2 registers, and we'll also be adding a status register as well, which we'll come to a little bit later on. But the mode control register means that our test program is going to need to make sure we set these values appropriately before we'll actually get any output. And in some of the earlier videos, what I've done is hard-coded some of these values. So I hard-coded the high res to be 1, and I hard-coded the video enable to be 1 in the PLD. And we need to now make changes to make these part of the mode control register. So now I'm going to go through some of the schematics from the original CGA card. So this is a project which I've referenced previously, and this has KiCad versions of schematics that have been converted into KiCad. So this shows the CRT-C controller, the video RAM, and the address latches and buffers. Then we've got the various attribute and character latches, the video ROM and the shift register that's producing the dot output that we covered in the previous one. Now, the reason why the original CGA card ran graphics modes in the 40-column mode was because it actually had 2 shift registers dedicated for serializing the graphics. I think this was probably because of the speed limitations of the video RAM it was using at the time. But with our design, we're not going to need to worry about that, and so it simplifies a little bit, and that's the reason why we run the graphics modes using the high-res 80-column mode rather than the 40-column mode. And the multiplexer here determines which colours are going to be output to the monitor, and the logic around here is quite complex, so I'm going to do a couple of slides where I've copied this and annotated it so we can actually explain what's going on there. There's then a number of pages of logic where various timing signals are produced, and again we'll be going through some of the logic in detail here because this determines some of the outputs for determining what video attributes and things we show. And it's a little confusing because the video attribute output is in actual fact squeezed in the top left-hand corner of this diagram, which is the main one with the video RAM and the CRT-C. So this kind of little bit gets snuck in the corner here. But we'll be going through this in a little bit of detail. Now, in video 53 of the original series, for which will be a link at the top right-hand corner here, I did go through these contents in a lot more detail. I'm just going to be doing a higher level view of it during this video. If you really want to know all of the gory details about all of these various signals, then please have a look at video 53 of the previous series. So this is the extract of the control mode register and the color register, and also some information about the color attributes. So on the original design, there were only 6 bits used for the mode register, and in fact it used a 74LS174 latch which had 6 inputs and 6 outputs. It did also have a reset, master reset, which was using the main reset line, so this would 0 on the system reset. And you can see here that there are a number of the pins. The high res is used to determine whether we're in 40 character or 80 character mode. This BW mode is used to turn off the composite color, whether we're running in grayscale or in color. Video enable enables the output or disables it so that the CPU can update the video RAM. We then have this one here, the 640 by 200 B&W is effectively the high resolution 2-color graphics enable. And then the final bit there is determines whether or not we have blink enabled or whether the attribute 7 bit is used for the background intensity. We won't worry about this bit down here too much. This is to do with the different color sets in the 4-color graphics modes, which we'll be covering later on in the series. Now this is the attribute byte values, so you can see here that the foreground color and intensity is on the lower 4 bits there, and then the next 4 bits have the background color, and depending on the blink setting here, this will either determine if the character will be blinking or whether or not the background intensity will be set to the high value. And this is just a note to a reminder that the B&W mode just disabled the composite color video output, which is primarily for composite video and TV RF modulators. So this color multiplexer is what actually a lot of the logic that determines the colors coming out here. So you have the red, green, blue and intensity outputs here going into the video output circuitry. And again, we've just got our attribute values here, so blinking or background intensity and all of the foreground and background colors here. Now what these 2 multiplexers, they are 4 input multiplexers with 2 outputs, and they're controlled by these 2 MUX A and MUX B inputs. So the S0 and S1 inputs here control which of the 0, 1, 2 and 3 outputs are routed through to the outside there. And there's one other signal, which again we don't need to worry too much about at the moment, but this strobe value here is when we're in the high resolution 2-color graphics mode, this strobe value actually turns the background color to black. It actually disables the outputs here, but we don't need to worry about that too much. And what we can see here is that the red values are coming from attribute 2, attribute 6, and is also coming from one of the graphics color signals, and also the overscan color value coming out of the color register. You can see the green values are similarly attribute 1, attribute 5, or the C0 output for the 4-color graphics, and also the overscan green value coming from the color register. Similarly for blue, the only difference for blue is that that cell blue that I showed on the previous page is used to calculate this value. There isn't a bit value to determine that, and in fact this is determined by which of the color palettes is enabled. And then the overscan B again comes from the color register. So you see that the text mode really is the foreground and background colors, and then these are related to the graphics modes. And then finally, for the intensity here, we get the text intensity from attribute 3, but then there's this logic here that says if blink enable, and this is the inverted blink enable in fact, so if blinking is enabled, then in fact attribute 7 does not make it to here, and this will always be 0. So in fact the documentation that's saying that the background intensity would determine this value is actually incorrect. It would require some extra logic in here to route the background intensity into here in the situation when blink was enabled. And attribute 7 is routed through here, so if blinking is disabled, then attribute 7 actually determines what this value is. So this is how I was able to determine that the documentation was not actually completely accurate. So background I does not affect the text mode. It probably would be better be called graphics intensity, for example. So then on this page, this is just summarizing the logic rules for how these mux A and mux B are determined. And fundamentally, mux A is 0 for foreground text, 1 for background text, and mux B is 0 for text and 1 for graphics. Now, really, this is more to do with the graphics, so we're not going to worry about this too much, but these rules and things here slightly more involved when we get into the graphic side of things, which we'll be covering later on in the series. But for the moment, all we need to really worry about is that foreground is 0, background is 1, and multiplexer B 0 for text. So this was the video output logic that I showed you, which was on the first page, and this is really the logic which is going to be encoded into the Complex PLD. In the first series, this was actually CGA Video Out PLD, and this has now been merged into our Complex PLD. And fundamentally what happens is that we have the various signals. So we have the cursor blink clock here coming in. There is the cursor signal coming out of CRTC, which has been delayed by 1 or 2 character clocks. We have the character generator dots, or S dots as it's known in some of the diagrams. We have the blink clock coming in here. We have the control register enable blink coming in, and we also have the current characters attribute 7-bit. So you'll see here that I've identified these in condition A, condition B, condition C, down here, and these are all implemented in the PLD logic. And I know that this actually works pretty well because in the version 1 of the Breadboard PC, all this appeared to be working. And the alpha dots output here determines whether we're showing a foreground color or a background color. So it includes the character generator output and also includes the blinking and also the cursor blinking as well. So this is a summary of the mode and attribute and control summary. So the control port settings, what the modes are. Now we're only going to be worrying about the 80-column text mode and the 40-column text mode for the moment. The graphics modes we will ignore for the moment. So we're only really worried about when the graphics bit is set to 0. When high res is 0, then we get 40-column mode. When high res is 1, we get 80-column mode. We also take into account blink enable. So if blink enable is 1, then we get the blinking background. If it's 0, then we use the 7th bit is the intensity for the background. And you'll see there that the 0 here indicates that that's what actually happens. It isn't background intensity like the document. Now what you could probably do is we could modify the PLD to actually implement that if we wanted. But part of what we're trying to do here is to maintain backward compatibility with the original CGA video adapters rather than fixing any of the inconsistencies that exist. And finally, the BW value, this is going to be used to switch our video digital analog converter between the color palette and the grayscale palette. So this will just, when it's 1, will just give us 4 grayscale values. So white, black, and 2 shades of grey. And by default, the cursor will generally be shown on the raster line row 7, although in fact, because we have double scanned our lines here, so rather than making the display up of 200 lines, it's made up of 400 lines. And so in actual fact, the row numbers will probably be something like 14 and 15. Now the overscan output, it will actually produce the overscan output, although it won't really generally be seen on the video adapters that I'll be using just because they don't generally show the overscan area. But if we're using this on a TV, for example, then the overscan color will be determined from the color register. And this is for when the display enable is 0 and we don't have the horizontal sync or vertical sync pulses. This will determine that overscan color around the edges of the display. There's one other bit that a number of the registers in the original design, where you can sort of see these pink bits, there is a clear shift register value, which is how the video enable is actually implemented. And what actually happens is that the video enable coming in here, that if video enable is set to 0, so disable output, then in fact this signal here will go low, which will clear the various latches and output shift registers. And the logic necessary for doing this is a little bit complicated, but basically what this does is it will set the clear shift register for 1 clock cycle at the end of each horizontal line, and it will also clear the output when video enable is set to 0. And there's a few delays to the various signals coming in here, which are part of this. But these rules have been implemented in the Complex PLD. And then this is just the character and cursor blink clocks. And these are based on the vertical sync clock coming in here, divided by 16 for the cursor blink rate, and then that is then divided by 2 for the character blink rate. So effectively, with the vertical sync of 70 Hz, the cursor blink rate is about 4 Hz and the character blink rate is about 2 Hz. And again, those original rules were in the CGA Blink Sync PLD, but that has now been incorporated into the Complex PLD. So this is the output that we had previously. So this is just our 256 character generator ROM values being repeated because of using the address lines. And in the previous series, the output that we got from there, we would expect to see the same characters, but with the color attributes changing behind them. So we'll have the foreground and background colors changing quite a bit. So this is what we got last time. It looks a bit messy, but what this indicates is that we've got our various character generator values coming out and that the colors are cycling through various values. So you can see that the foreground colors are going through to black and white and all these other various colors, and the background values are also changing as well. So let's have a look at the KiCad schematic and look at what we need to wire up. So this is our Complex PLD here, and we've already wired up quite a few of the signals. There's only a few of them that we're going to need to wire up in addition here. So we are going to need to wire up the data bus going onto the side here. So we've got D0 to D7. We're going to plug this into the data bus that we've already got going to the CRTC and the video digital analog converter up there. And then we've got a couple of the I/O select lines, so the CGA status register select, the control register select, and the color register select. We need to have those feeding in there so that our PLD knows when we're reading and writing to those particular registers. And then we're going to need to connect the color outputs here. So the P0 to P4 color outputs are going to feed into our video DAC here. Now, up till now, we've just been feeding the inputs here either from the address lines here to get our different color bars coming out, or in the previous video we just toggled the P0 value would be toggled by the output of the character generator. So down here where our S dots came out here, we just hooked that into P0. But what we're going to be doing in this one is the video digital analog converter is going to be controlled by the outputs coming from here. So now we're just going to go and wire those up. There's not too much to wire up there, so it should be fairly quick. And then we're going to need to look at the PLD rules for actually configuring all of this. Okay, so let's wire up things first. We just need to do the cursor, which needs to go over to the PLD here. We'll just check what that is. Pin 83. Now the CGA color control status, that is going to 57, 61 and 63. That's 61, 63 and 57. Now we need to do the P0 to P4 is going up to P0 to P4 here, and this will be 96, 97, 98, 99, 100. So the 97 and 99 are odd, and those are on the outside, and the even ones are on the inside. So we'll just remove the hard-wired ones, and we can take our alpha dots output off there. So I've got a two-way and a three-way there. So the two-way goes on the outside and the three-way on the inside. We just need to get enough space to plug these in. Okay, so those are plugged in, and we just need to make sure the purple is the lowest pin. Hopefully that will be okay. We need to wire in the video data. The video data is down the bottom, 37, 36, 35, 33, down to 29. And there is the VCC power rail in the middle there, so we just need to be careful with that. And we're just going to wire those in, as we've done previously, up to the address lines up here, just to give us values going from 0 to 255. So I've got the cable here to plug in up the top. I just need to plug in these down here, which will be a little bit fiddly. It might take me a few minutes to do that. Okay, so that's the video data hooked up there. So I'm just going to hook those up to the same address lines. There we go. So just need to do the data bus. I'm just going to pull this one out from the programming leads and there's the data table, pin one down the bottom, and we just need to put this over to the data bus over here. Finally, we just need to make sure that the alpha dot is connected to the output from the shift register. So we no longer have the shift register going straight into the video DAC. It's going to go into our logic circuit here, and that'll eventually make its way out there. So, okay, so that's all plugged in there. What I might just do, in fact, is I have got this test board here. So rather than plugging in the attributes into the output of the CRTC, I might just plug it into this board, and it means I can then just vary the inputs by the dip switches, so I can actually go through all the colours individually. Might be a little bit easier to see what's going on. So I'm just going to take the attributes out of there and plug it into this little board just down here. That's all done. So now what I need to do is to sort out the programming. So I've got the programmer plugged in there. We just need to now look at the PLD configuration. Okay, so here's the PLD. This is version 5 now, just been a few changes since the last version. So you can see up here we've plugged in our P0 to P4, which are the video outputs. Also plugged in the cursor and the CGA color, CGA control, CGA status, and we've also plugged in the video data down here just so it's giving us some values from the CRTC address lines. These are all the pin definitions. So first of all, we've got our color register. So the color register D latch inputs are defined as the D0 to D5 IO. So we need to use the IO because the D0 to D7 pins will be used for input as well as outputs. So the IO can be used when it's an input and the output enable is disabled. Then the clock is the CGA color clock. And because this is an active low signal, but we're not using the reverse polarity, this means that on the rising edge of that at the end of the signal, then it should clock the data register value into the color register, and then the reset is going to reset that register. So the video data here, the VD0 to VD7 is the internal latched video data. The VDIO is going to be used for the input and the output, in that we will be using that to write to the video RAM as well at some point in time, but not quite at the moment. So we're taking the I/O pin for the video data input, we're mapping that to the video data latched, we're clocking it on the attribute shift register latch. The only thing we need to check is whether or not we need an exclamation mark in there or not, and that will determine whether or not it will latch it at the beginning or the end of the pulse. At the moment, the output enables are hard-coded to enabled. We will need to change this once we enable the video RAM writing, and the registers are cleared with the clear SR value that we talked about earlier. So our dot clock and our QA to QD, which are divided by 2, 4, 8 and 16 clock signals. Then we've got our various character clock, character latch, attribute shift register latches, which have got quite complicated rules, but those have come from the previous series, so we shouldn't need to change that. We may need to tweak them a little bit later on if we find there's some problems. Then we've got our horizontal sync and vertical sync values, and the horizontal sync will actual fact be inverted because we have the invert bit set there. Then we have the vertical sync, and the vertical sync is in fact divided down by these registers here. And then we have the blink clock and the cursor clock set here. Then we've got our control register. So again, the control register latch values are being set by D0 to D5, the I/O on that, and they're going to be clocked on the CGA control. Again, we might need to check to see if we need to put an exclamation mark in there, but we'll try it as it is first. Then we've got some of the color graphics values, which we don't need to worry about at the moment. Then we've got our intensity red, green, blue values, which have been worked out by the various alpha dot values and the foreground and background. So when we're in text mode, for example here, so not graph is text mode. If we have the alpha dots is true, then we take the foreground color. If alpha dots is not true, then we take the background color, and also we take into account the blink enabled as well, in that the intensity does not actually count when we have blink enabled. And then the red, green, blue are very similar, apart from, of course, they don't care about the blink enable because they will just use the 4th, 5th and 6th bit rather than the 0, 1st and 2nd. Then we've got our attribute 7. So when we have text mode and blink enable, then this will be set when video data bit 7 is set. So this will determine whether or not we will have blink enabled. So then these values relate to the logic that I showed earlier. So the C gate is a combination of the blink clock and the blink enable attribute 7 and the cursor. Alpha dots is a combination there. So you can see here that we've got the gates A, B, C, which were in the diagram. So they refer to this diagram and the conditions in it. We've got our clear shift register conditions there, the overscan condition, and then these ones here are related to the 4 color graphics, which you don't need to worry about at the moment. Now these are the P0 to P4 derivations. Again, the rules here are quite complicated, but in text mode it's actually fairly straightforward. In text mode, so not graph, then it's the intensity, the red, green, blue. All the other issues are taken care of in the earlier logic. And we're also setting P4 to be the black and white bit. So when this is 0, we get the color palette values. When this is 1, we'll just get the grayscale values. Then down here, we have to set the output enable for the data lines to be disabled unless we have CGA status. If CGA status, which is active low, goes high here, then the output enable will be enabled. Otherwise, it will be disabled. And then the I/O lines will be used elsewhere. And then in this case, D0 is going to be the blank DE signal. This is the inverted display enable signal. This tells the PC whether or not it's safe to write to the video RAM without causing interference. These values, that's just going to be 0. This is set to 1. This one will be set to the vertical sync. Again, we can tell when the vertical sync interval is. so that the PC will only update the video RAM during the frame refresh period, and these other values are just going to default to 1. So that's the rules. We'll just need to now compile this using WinCPL. Just reload this. That should have compiled and the fitter should have run. We just look at the fitter output file. That appears to have run. We just check the end to see if it's worked. Device fits. We can see here we have the statistics for how many logic cells and pins and things we're using. You can see the fan in here on the block A is still quite high. There's only I think 40 fan in. So that's quite high, but this appears to fit. And if we just check the pin out, so you can see the pin out, we've got D7 down to D0, CGA status, control, color. So, and we've got the P0 to P4 up there. That just means that we should be able to check these signals. And we can also see that there are a few signals on the output pins as well. The video enable, blink enable, the black and white 640 mode, high res, graphics mode. You can see that some of these other control register values are available on the outside here, so we should be able to test those. So we just need to program that now. To have the ATM ISP, just going to erase the chip first, just because we found that it was necessary to do this. Under some circumstances, the pin 99 and 100 weren't being set. And since these are important for our video output, then we're just going to make sure we're going to erase this first. For some reason, it always fails the first time, but always works the second time. That's finished. Now we just need to create a new version 5 file here. And if we see here, at the moment, it's still using CGA video 4.jed, so we just need to change this. Change it to version 5.jed. Program verify. Okay, so now we should be able to run this. We'll just save our file there. We'll just run this, it'll take a few seconds to do that. Okay, so chips programs. Okay, so now we're ready to test this. So I'm just modified some of the software slightly. So this is CGA Test 2, so it's based on the Test 1 that we used last time. Just a few changes. I've adjusted the vertical sync timing. Sometimes the display was losing sync. And I've also changed the palette 1 item that we changed to white in the previous video. Changed that back to blue so we can get the proper colours. So you can see here that I've actually changed total adjust for the vertical was 3, now it's 1. And the sync position I've changed from 1A to 1.9. So it just means that the output fits a little bit better. So just need to assemble that. We're just going to switch on the Breadboard PC and load that and run it up and see what we get. So I'll just show the video on the side there. So I'm just going to put it in 6000, code segment 6000, load, and we're just going to send the updated program down. Okay, so I'm just going to run it now, and we should then see something in the video on the right hand side there. There we go. So that is the basic pattern that we had last time, and the reason why I've got that is because I've actually got the attribute set to 0s for the background and all 1s for the foreground, so that should give us white on black. So if we just go to the full screen now. So if I now change some of the dip switches here, so if we perhaps change the background to blue, and then we'll change everything else in the foreground to black. Okay, so we've got black on blue, we have blue on blue, not very useful. So if we change the background back to black, then we've got blue on black, green on black, red on black, and then we've got the higher intensity. So if we have blue and then we do high intensity, it's a bit lighter, green, green high intensity, in red, red high intensity. Then obviously we can try the various combinations. So this is blue and green. should be orange, magenta, and that sort of light grey. And if we then bring intensity in, then we get white. So there's not a big difference on this display between the two colours. We might need to adjust the constant current source so we get a slightly bigger difference. And then we can also then try out the background colours as well, make sure those are working. So I'm just going to set this to white. Then this is the blue background, green, red. And then at the moment, blink should be turned off. So when we turn this on, we should then get light red, light blue, light green, and then other combinations. That's yellow. That appears to be working. What I'm just going to do now is to switch the attributes over to the address lines coming out of the CRTC. So we'll just see if we can get the output that we had previously. You can see that all the characters are coming out correctly. I just now move the cable over to the output of the CRTC. So we can see the colours are coming out, but the text is not quite right. I suspect there might be something interfering. If we put this back again, so the characters are definitely there, but when we plug the attributes into the same address lines, then it changes for some reason. I might need to look into that, but this is just a test pattern, so we're just trying to make sure that we're actually getting something sensible coming out of here. And if we change it to some of the other address lines, then we can see that we are definitely getting some sort of output there. That probably looks a bit better. I think we can see there we've actually got the character coming out there, and that probably looks a bit cleaner. So it's not quite the same as the test pattern I had previously in the previous series, but you can see here that the colours are slightly broader band. Probably makes it a little bit easier to see the differences in the colours. Okay, so we've got a test pattern which is showing both the characters and the attributes. Occasionally we are losing synchronization from time to time, so I'll need to look into that. So we've now got the attributes working, and we configured the PLD for the color register, control register, and status register. Now I need to do a bit more testing on that, and I need to update the test software to actually test all the attributes. So in the next video, we're going to do a bit more testing of the attributes and the blinking and things like that. And then we're also then going to add the video RAM and add the address latches and buffers to the video RAM, and then see if we can actually get some test patterns programmed on the display like we had in the previous series. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to more people. Thanks for watching.